Hi folks, Dr. Pingle here. Just a quick lesson on Lidar ground filters and Lidar data. Since there are a few people in class that have not had a chance to play around with this kind of data yet. And I want to make sure you're getting the most from your readings this week if you've had a little bit of experience. So, this is one way to get Lidar data. I'll publish some links in class and send those around. But the easiest way to get Lidar data is actually just through the national map, like you'd get a lot of other data. The 3-depth program, the elevation source data, is provided over the national map. But occasionally, states will provide their own portals to download data as well. So, Region provides data through an ArcGIS map. Illinois Lidar data can be downloaded through one of their own websites. So if you go to data, there's a whole list of that stuff here. So it varies a little bit by state. If you can't find what you're looking for on the national map, that's often a good spot. The other one is NOAA's elevation inventory, which is here. And so this can sometimes be a good place, especially if you're looking for coastal data or data near waterways. But my first stop is almost always the national map. If you want to look for a place, you can look for something like Blacksburg and zoom in. And then what you would do is you'd look at elevation source data. So a lot of times in this class so far, we've been talking about elevation products, DEMs. You can get 1 meter DEMs, which would have been LiDAR-derived DEMs in most cases. That's not what we're interested in. We're actually interested in the raw LiDAR data. There is a note here that says FTP links won't work on Chromium browsers. This seems to be true, and Edge doesn't seem to be any better for whatever reason that seems to want to open things in Chrome. You can still access this stuff through an FTP client, I use a client called FileZilla, or any FTP client will do. This is a fairly temporary condition. This didn't happen the last time I was looking at this, and probably they'll get this patched up soon enough. But in any case, you may notice that some of your downloads aren't working, and I will provide a LiDAR tile for you to work with this week. All right, so if you show where you can get these LiDAR point clouds, the map will turn green where that data is available. I'm going to go ahead and hide that and just do a search for products right here. Remember that LiDAR tiles need to be pretty small. They're quite data heavy. Just in this little window, there are 12 of these. Each one of these is, I don't know, probably on the order of 30 megabytes or so. They try to parcel these things up a little bit so that it doesn't get too unwieldy. You can show all the footprints if you're interested, and you can see these over here. And as you mouse over, you can sort of see which ones are which. If you want to download one of these ordinarily, you just click on this link. You can see that is not working. So you could copy this link address and paste it somewhere else if you wanted to. One thing that you can do, this is something that I use once in a while, is Linux has wget, so you can use the command wget on the Linux command line, put in the file that you're looking for, and it will download as well. So I know that happened pretty fast, but this is a recording. You can go back and you can look at that if you're more interested in that. Suffice it to say, most of the time you should be able to get to these in a web page. It's acting a little strange right now. But there's always other ways to get the data that you might need. So once you have some data, how do you look at it? Well, I like to use a program called Cloud Compare. So Cloud Compare is open source software for LiDAR data, relatively well supported by industry, thankfully. It's a really useful program. You can download it for free. I would recommend downloading the latest stable release. The stereo version is pretty cool. If you've got an Oculus Rift, you can actually immerse yourself in some of these clouds and work with them there. But otherwise, if you don't need that feature, then the Windows version is fine. It's a relatively small download. It installs pretty well. It looks like there are some issues with ATI and Intel graphics cards, which you may want to be aware of. But most of the time, this works pretty flawlessly. So that's great. I've got mine set up to load these automatically. So you may be able to double click on it. You may have to open the program and just drag it in there. The files that you download while this is loading are usually going to be LAZ files. Sometimes they will still be LAS files. LAS is the ASPRS standard for a Lidar container. It turns out that specification is just a little bit inefficient, and so there were two attempts to compress those. One is called the LAZ format, invented by Martin Eisenberg. It's a great format. It's seen a lot of universal adoption. The other one is a ZLAS format, ZLAS. That one is Esri's compressed format. After a couple of years of sort of getting a little popular, I think that format is probably dying off at this point. The Lidar community has more or less decided that it wants to keep the containers non-proprietary. So it's likely that the LAZ format will continue to stay pretty dominant. And those files are about 1/6 or so the size of a regular LAS file. When you open a Lidar file in Cloud Compare, you're going to get a window that looks like this. Lidar is more than just XYZ coordinates. It actually contains information. It may include visible light information, so RGB. This particular file doesn't, but some of them do. Sometimes it will have a classification, which is actually the subject of the class today. So how to figure out which of the points in here are what, and there's a whole list of different kinds of things that points can be labeled as: vegetation, water, noise, ground, and so on. And we're mostly just going to be talking about ground classification today. But lots of other information gets tagged on to each point that you're looking at. The most important ones, you can look at any of these if you're interested. The return number can be interesting, so you can get more than one return off of a single Lidar pulse, and so you can keep track of how many pulses came back or how many returns came back after that pulse, what the first one was and what the last one was. That's conventionally what's retained, but you can actually get more information than that. Information about the flight line, all of this kind of stuff. We don't need any of that, but I do want to keep the classification and the intensity value for now. If you just leave all of these checked and hit OK, that's totally fine. It'll come right in. Because LiDAR data is often supplied in coordinates that are not latitudes and longitudes, it's a lot more reasonable to keep track of these things in some kind of a metric-like coordinate system, distance-based instead of angle-based. And so most of the time you'll see these things distributed in either some kind of a state coordinate system or a little more commonly probably UTM. Both of those are fairly common. You will sometimes see LiDAR data distributed in feet. You will more often find LiDAR data distributed in meters, but that depends very much on who collected the data and how they wanted to keep it. So this is, when you load that data up, what it's going to do is it's going to sort of create a false origin based on the actual data range in here. So an easting and a northing, those numbers can be quite large. And so typically what we do is we just recenter the cloud. This doesn't damage or delete any information. All of this offset information is retained. So you can pretty safely just hit OK. You get a list of the number, as it's reading into the file, it reads the header first and it knows that it's looking for about 23 million points here. Depending on your computer, you may be able to handle this many, you may be able to handle a lot more. I think the biggest cloud that I've opened in Cloud Compare is, I don't know, a little bit south of 1 billion points. It starts to drag a little bit at that level. If you brought in your only just the fields that I mentioned, you're going to get a cloud that looks like this. If you brought in some of the other things that may look a little bit rainbowy, in both cases, so right now if you click on the file it opened, it's going to be colored according to some scalar field more than likely, and that scalar field is going to be indicated here. So because I brought in classification and intensity, I'm right now looking at intensity. That was the first one. But you may be looking at something weird like scan angle rank or something like that. If I want to look at this stuff sort of and view it by its height, which is actually probably the most common, we have to take the physical coordinate and we have to turn that into a scalar field, and that's sort of a peculiarity of Cloud Compare. But it's very easy to do. You go to Edit, Scalar Fields, and then just export the coordinate as a scalar field. And most of the time, you're going to want to do this with the z value. But Cloud Compare is agnostic about the coordinates. If you wanted to color this by the x coordinate, you could do that. It would look strange, but you could do that. So we'll just hit OK. So this is probably what you're more likely expecting to see when you open LiDAR data in Cloud Compare. And so that's almost always the first step, is sort of converting the coordinate to a scalar field. And if we manipulate this, you can start to see the 3D structure. I think this is a water tower on top of one of the hills near Blacksburg. Little ravine down here, some big forested area, and so on, some houses and trees. It's a little bit hard to make out, and so there are a couple things that you can do to sort of make things a little bit easier on yourself. One thing that you can do is to turn on a shader. So if you go under shaders and filters, you can turn on the EDL shader, and you'll start to do sort of like a hill shade replicant, so that sort of looks a little bit cleaner. All right. The other value that you might want to look at under scalar field is the intensity. So that's what was loaded at first. A LiDAR return is going to include information about the strength of that return. This generally mimics, to some extent, the visual lightness or darkness of the material. So if it's a white object, it'll tend to reflect that light back more. If it's a dark object, it'll tend to reflect it less. And so sometimes what you see here looks a little bit like a black and white image. It's a little more complicated than that, because things like the angle of the return can matter, the complexity of the surface. If it's a rough surface, it won't return as much as a smooth surface. And so it's not a perfect mapping of sort of like a grayscale of the RGB, but it still looks pretty good, and it's fairly intelligible, and I would encourage you to use that sometimes when you're working with LiDAR data. We're going to talk about classification, though, today, and one of the things you might very well want to do with your LiDAR dataset is to turn it into a terrain representation. So you can see that LiDAR includes returns in the environment with all kinds of things, trees and houses and all of this stuff. And so for this reason, this is really one of the things that makes LiDAR so valuable. However, in some cases, you may want to throw some of that information away, and so you can actually just remove. You can remove some of this stuff, or only visualize some of this stuff with a classification. Now, LiDAR data by default is not classified when it's collected in the airplane. It's not classified, but it's always sort of subsequently processed by whoever is the contractor. These days, it would be very, very strange for that contractor not to provide a pre-classified point cloud. It's only going to be classified a little bit, but you can be fairly sure that one of the classifications that's going to be present is whether it's going to be which points are ground and which points are not ground. If you look at the classification, you'll see something that looks like this. Now, it's a little bit difficult to see, so we've got a color scheme that's kind of set to go from blue to green to yellow to red, which is great when you're working with something like elevation information, right? So that looks fine. But these sliders down here, so here's a histogram of the elevations, and you can kind of move these sliders around to sort of bring out detail or enhance contrast if you want. So pretty easy to do that. These will sort of make things gray or not. So you can see that anything above that line is going to be gray, and anything below that is going to be same thing down here, right? You can make the bottom gray, and it gives the ranges. So it's a really easy way to sort of look at this stuff. But again, we're going to look at just the classification. So classifications are given numbers. So what we're interested in is classification band 2. So you can see that we've got some stuff over here that's 1. We've got some stuff over here that's 7. These are common designations. So these are kind of what you're looking for. 1 is unassigned, 2 is ground, 7 is noise. So these are the 3 that are sort of in our data set. But there's a bunch of other stuff too. That's a pretty normal classification to get from sort of this this big database, is just sort of ground or not ground, or in some cases noise, and that's about the most it's going to be classified as. So in this case, we could move the slider down here, which would help highlight some of our noise if we have some. So anything that's kind of being shown here in red would have been classified as a 7. More importantly, though, what we really care about is this 2 category. So I'm going to just kind of move my sliders here so you can start to see it this way. So anything that's in blue are things that have been identified as ground, and anything that's in gray is anything that's been identified as not ground. I'm going to zoom in on an area here. And there's some really nifty tools in here that you can use. I'm just going to grab a little section and pull that out. All right. And if you hit this kind of 1-to-1, then it kind of recenters it a little bit. So, this is a little bit more manageable. You notice as we zoom in, that point size is a little bit small, so you can go down here and change that to something else to kind of make it pop out a little bit. So we're seeing these things rendered as little squares, little 3D squares. All right. So again, blue is ground, gray is not ground. So the gray is certainly picking up these trees and it's picking up these houses, but you'll notice that it's also picking up a lot of things down here, right? So what we would ordinarily think of as ground, there's definitely blue in here, but there's also gray. So there's pixels that are ground that have been classified as not ground. So this is a particular kind of error that we would like to avoid, but we would also like to avoid anything. We don't want trees classified. We don't want the trees to turn blue either. So we can kind of make mistakes either way. So we can call something that is ground not ground, or we can call something that's not ground ground. Easy mistakes to make. A couple of other things that I'll highlight here. One is that the Lidar is taken from an aircraft generally flying relatively high. And as a result, it doesn't usually hit the sides of buildings, so these rooftops are sort of disembodied a little bit. You can see them kind of floating, so this is kind of an interesting peculiarity of Lidar data. It's got these big holes in it on the ground. And so this is the kind of thing that if you remove the top of this, you've got to fill this in if you want a terrain surface. And so this is where you'd use in painting or other techniques to kind of fill those gaps. And trees can have a similar effect, right? So at the bottom of this tree, we've had enough returns in here that we're sort of missing a lot of ground points kind of in that area. You can pick up some other detail in here. For instance, we've got what's probably a street running through here, so you can sort of see the visual seams in there. You can also see some artifacts of the collection. So the direction that the aircraft flies will sometimes produce some artifacting in here. So you see these sort of parallel lines that are a function of the scan itself, probably, and not anything on the ground. So artifacting in here is not so uncommon, and it's just something to be pretty aware of. This is the kind of thing that could throw off subsequent analysis if all of this were included as a ground surface. Those would be producing some weird sort of quantitative effects in your resulting cloud. So good to be pretty familiar with the data before you start talking about how you use it. It may be sort of surprising what's in here and what's not in here. So the software that classified this as ground and not ground, you do not have to accept that classification. This week it's all about different ground classification systems. we'll talk about the issues. I provided a reading on mine. Cloud Compare has a built-in one called the CSF filter. So this is a cloth simulation filter. Pretty interesting, neat idea for ground filtering. And you can see that it's got a link to the MATLAB page and a link to the original paper up here. Really, really handy way of dealing with this. If you want to read more about it, maybe in a future iteration of this class, we'll include that as a required reading. But the gist of it is essentially imagine you're laying cloth over it, and anything that's where the cloth is kind of getting hung up and getting wrinkled is essentially something you don't want on there, right? So it's sort of looking at the simulated surface and looking at the patterns associated with it, and from that it can kind of tell what is ground and not ground, or maybe can't tell, but maybe can make a guess. Now you'll notice that there are some parameters in here. We've got whether this is a steep slope or relief or flat. So how you answer that question is going to improve or worsen the processing. We can do things like set cloth resolution. This classification threshold is fairly common. So once it kind of makes its test, it's going to say anything within 0.5 units. If your point cloud is in meters, then it'll be 0.5 meters. If it's in feet, then it'll be 0.5 feet. Will be classified as ground. So it's pretty interesting. You can export the cloth mesh. This can be handy if you need sort of the resulting surface and don't want to reinterpolate it. Lots of neat stuff here. So we'll just accept some of the defaults here and not fiddle around with it too much. But I would encourage you to play around with those and sort of see what they can do. So we are going to run that, and let's take a look at the result. All right, these are our ground points that our filter has come up with. These are all of the things that our filter thinks are not ground. And you can see that it did a fairly bad job, right? We did find some things that are not ground, that are ground. Those indeed are probably almost surely ground points. So we had very few errors of commission, but we had a lot of errors of omission. We're missing a lot of things. We're missing a lot of ground over here that should have been identified. So we're gonna nix those back out again. Make it one more go at this, right? So start this up again. Let's try adding this checkbox and see how it goes. All right, how did we do? A little bit better, right? So we've added some more points here by changing the parameters. We've now got a lot of these central points, but we've got this big swath in here of fairly dense trees. Essentially, is making it a little bit difficult to do that. So not a bad second run. So we'll keep that on here, and let's maybe take a look at these. So cloth resolution. The grid size, the bigger the cloth resolution, the coarser the DTM that you're going to get. All right, so maybe ours is a little bit too coarse. So maybe we make that 1. And then the classification threshold is set to 0.5. Maybe that's a little bit too robust. So maybe we turn that up to 1. You'll notice that we've got a bigger surface, so it took a little longer to calculate. These are all the ground points that we detected. All right, so now we're getting a much fuller picture. You can see the holes where the buildings are, so it's doing a good job there. But we've actually got the reverse kind of error. So now you can see that we're actually leaving a lot of these points that ideally we probably wouldn't want to leave, right? So we've got now some errors of commission. We are identifying some things as ground that are actually not ground. Right, it's a very different kind, but far fewer of the other kind of error. In general, this is a bit of a trade-off, right? So there's our ground points. In general, this is a fairly common problem. There's a bit of a trade-off between the one kind of error and another. Ideally, you want to do the best on both of them. And so that's kind of where the craft of algorithms come in. How do you more finely distinguish between these things in a way that minimizes both categories, ideally? And so some algorithms are better at that than others. So there's a quick introduction to both getting LiDAR data, looking at one processing visualization toolkit called Cloud Compare that I find very handy. Lots of other great tools out there. ARC has some tools that are okay. Las Tools is very good for processing efficiently. And PDAL is a relatively recent processing pipeline. Those are kind of the main ones, and then you'll often find TerraScan has some LiDAR processing things. With the Lidar 360 is particularly good at sort of some forest-based measurements and things like that. So there are a lot of tools out there, but Cloud Compare is one of my favorites. And then just a little bit on exploring one of the ground processing algorithms that you can use. It's a fairly popular toolkit, popular in large part because it's integrated with Cloud Compare. And you can see that by changing the parameters a little bit, you can very much change how the ground classification outcome happens. So thanks everybody, and we will see you in class.